Hi, my name is Steve Miller. I'm a professor at Williams College, and this is day 2 of the Teacher as Scholars session. And so what I want to do for this part is talk a little bit about cryptography. So the slides I'm using here are from some talks I gave for a wonderful program I'm working in, which is designed to try to get computational modules into the school curriculum. And we've worked with teachers at the high school level, at the elementary school level. And if any of you are interested, we have a whole slew of modules. We also have classes that we run for continuing education, where we are often able to give stipends to teachers. And so if any of you are interested in more information, please let me know. I'm happy to chat about stuff like this. But there's a lot of material available. All right, so, okay. So the first is I want to talk about some old ciphers. Now, we could spend 2 or 3 days talking about all the different schemes of encryption. One of my favorite stories is that they used to take slaves, shave their heads, write a message on their head, let the hair grow, and then send the slave out as Now, I'm not sure if this is true, but let's assume it is. What is the problem with such a method of encryption? This might be suboptimal. So people think that this is a good idea. We'll shave heads, put a message, let the hair grow, and then send it out. So there are 2 major issues with this. Any thoughts about what some of those issues might be?
Takes too much time to wait for the hair to grow back.
Yeah, it takes too much time to have the hair grow back. We don't have any miracle potions. They especially did not have them in the ancient world. So that's one. Although maybe you could do a wig. Anybody have any idea about what the second issue is? What happens if the other side intercepts the slave? Can they decipher the message? If they know that the encryption is just shave the head, write the message, then they just have to shave the head and they have the message. So when you encrypt, there's a couple of key concerns you have. You want to make sure that only the intended recipient can decipher the message. You also want the encryption to be secure, and you want it to happen in a reasonable amount of time. So for example, in World War II, when we're planning the invasion of France, Operation D-Day, this is an operation that was planned over months. So whatever encryption was being used had to be secure for on the order of months. Conversely, in the Pacific, if you've ever seen or read about the code talkers, the Navajo Indians, they used Navajos to talk in real time because essentially no one outside of America knew the language. And so in a situation like that, you want to be able to communicate very quickly. So being able to talk in real time and not spend the time to encrypt and decrypt, it was extremely valuable. If you're sending messages such as the enemy is over here, change your guns 45 degrees this way, shoot a little further, it's okay if the enemy cracks the code in 4 hours. In 4 hours, that information is no longer important. So depending on what your problem is, there will be different levels of security that you need. So I'm going to start off with a little bit of talk about how we're going to do things. So we'll start off by sending letters to letters, but later we're going to send, instead of letters to letters, numbers to numbers. As mathematicians, we like to work with numbers. You can have operations on numbers. What is 3 plus 5?
8.
8. What is C plus E? You can't really add letters the same way as you can add numbers. But if we convert each letter to a number, then we can do mathematical operations on them and then just convert back at the end. So the first encryption function we want is it's going to take letters to letters, and we want different letters to go to different letters, and we want all letters to be hit. So can someone tell me why we would want different letters to go to different letters? So what would happen if when we encrypt, both a C and a D are encrypted to the letter Z? If we receive a message with a Z, would we know where it came from? We wouldn't be able to decrypt it. So it is essential that different letters go to different letters.
So how do you decide which letters go to different letters?
Well, so that's where you have the freedom to choose. As long as we send different letters to different letters and all letters are hit, then we have a valid encryption scheme. So this is called an alphabet encryption. And you often see these in newspapers as the cryptogram challenge. If they give you spaces, the cryptogram challenge usually isn't too bad, especially if there's the I or the A as a separate, lone word. What's the most common word? Well, we'll get to this later. So it turns out that we actually don't need both of these conditions. There's only finitely many letters. So if different letters go to different letters, that means every letter is hit. There's no way that a letter could be missing. So as a nice homework problem, try to prove that we don't need this. A lot of times when we're doing things with students, for ease of exposition, we often put in more conditions than we need. And I think that's perfectly fine. But then as a nice advanced problem, you can ask them, do we really need all of this? Or as long as different letters go to different letters, does that mean everything is hit? So our setup is going to be X will be some input letter, and f of X will be the output, will be the encrypted letter. So here is a possibility. The simplest function I can think of is the constant function, f of X equals C. So that means no matter what input letter you send, it always gets encrypted to the same letter. Well, we talked about why we can't do this. You would just get, no matter what message I sent to you, you would always receive maybe Z, 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 Z. So this function is too simple. So the next simplest function is we take our input letter and we just add C to it for some constant. So what I'm really doing here is maybe think of A as the number 1, B as the number 2, C as the number 3, and we're just shifting things. And what I like about this is we start by taking, what's the simplest function we can think of? It's the constant function. Okay, unfortunately, it's too simple to do good encryption. So let's try the next simplest function, a linear function. What might you try after a linear function? So can you guess what we might study later in the lecture after we successfully study the linear function?
Quadratic?
Yeah, quadratic. And so you can ask your students, what do you think we should look at next? Do you think that will be a good idea? And so going back to the time of Julius Caesar, the canonical standard example is to take C to be 3. And so we shift every letter forward by 3. So A goes to D, B goes to E, W goes to Z, and then we wrap around. So if you shift X by 3, X goes to Y, Z, A wraps around. So this is like clock arithmetic. It is almost 10 o'clock now. In 5 hours, 10 plus 5, it's not 15, it's going to be 3 on the clock. So most students have experience with clock arithmetic. This is all we're doing here. Now, in some sense, what I love is when you read about this in some of the books, they say there was really no need to do this because so few people could read back then. Just writing down the message was enough. But let's have a little extra security. So with this little extra security, do you think this is going to be easy or hard to decrypt? How would you decrypt this message?
You just undo that one wrapping around.
So how would we uncrypt? So if we receive the letter E, how would we decrypt the letter E?
The 3 letters.
Right, which way do we move?
Back.
Backwards.
So instead of adding 3, we just subtract 3. So it's really not that bad. So here is the conversion table. There's really no need to write it down, but if I get the letter M, M goes to P. So if I receive a P, then it was the letter M that was sent.
But isn't the problem with that is that, vowels show up all the time, and in short, like in the letter, if you encrypt the, and I don't know, it just seems like,
Well, Henry, that's a problem for later.
okay,
This has an even more serious problem than that.
okay,
There's only one shift, right?
right,
Once I figure out how anything is shifted, I know the entire message.
right, yeah, that's what I mean.
So this is just writing things in a circle just to really emphasize the wraparound. And so if I gave you the message meet at 10, I convert all the letters to numbers. I then add 3 and I get, and then to decrypt, you would just subtract 3. You could actually write something in Microsoft Excel to do this. And so this could be a nice opportunity to give students some basic programming where they don't maybe have to use something too extensive, Google Sheets as well. Can you set something up? And then the hardest part would be, how would you convert the message from letters to numbers? Can you actually do operations on letters? And so these are great things for the students to explore. All right, actually, before we get to the more complicated one, let's just talk a little bit about how to decrypt this. Imagine you didn't know that the Caesar cipher was to add 3, and you received the message, but you know that it was encrypted with a Caesar cipher. How long would it take you to decrypt?
Not long.
So quantify not long. I'm a mathematician. I love numbers. How many at most?
One, two, three.
So you don't know what it was shifted by. How many attempts would it take you at most?
Oh, I see. Yeah.
6.
I'm sorry?
6.
Why 6 attempts?
Because the numbers are, the letters are repeated.
Okay. But we don't know what the original message was. Maybe the original message was moon at ton,
Oh, gotcha.
right?
Hmm.
So we don't know anything about letter frequency, but I'm just saying, assume the worst case. And sadly, with all the coronavirus updates, we keep getting a lot of stuff on worst cases, but let's do a worst case here. The worst case here is not going to be too bad. How many possible shifts are there?
26.
26.
6. So worst case, how many things would we have to try before we got the answer?
25.
25.
25.
Right, because the message is almost surely not a shift of 0.
Right.
Shift of 26, because then you would just be sending the original message. So we
But when you, as you start going through the 25, would it take you, it wouldn't take you all 25 attempts, would it?
right, what you would do is you would just start changing each letter, and you would see, does the beginning look like a real word? And so
Right.
we start off with the PH and we subtract 1. If we see that it's not looking like a real word, all right, then let's subtract 2, let's subtract 3, let's subtract 4.
Right.
You don't have to do the entire message.
Right.
And so because there's only 25 things to try, this is not that secure if somebody knows that this is what's being done. If you don't know that this is being done, then it's a little bit more secure. So now let's get some more mathematics. Before going all the way up to quadratic functions, we could try a more complicated function. So now let's try a general linear function, ax plus b. So before we did the special case when a equals 1, now we're going to allow a to be any integer. And then the question is, what possible values can we take for a and b and have something that works? So b is actually going to be very easy to understand. All b does is shift everything. So it turns out all values of b will work. If a is valid, all b does is just shift things at the end. And so you can almost view this as 2 different encryptions. You first encrypt by sending x to ax, and then you do a Caesar cipher and shift it by B. So this is an opportunity to talk to your students about breaking a hard problem up into smaller, simpler ones. If we first look at shifting X to AX and then shifting by adding B, we've reduced the general problem to two simpler ones. And that's a wonderful concept to do. This is actually one of my favorite problems in the cryptography book I wrote. Somebody is worried that the Caesar cipher isn't that secure. So what they decide to do is they choose 17 different numbers. And they do 17 different Caesar encryptions, one after the other, after the other, after the other. Is this now more secure?
So,
I see somebody shaking their head no. Why not, Dana?
I'm just thinking if you're using the same pattern over and over again, they're going to get it.
Well, but first maybe you shift by 3, then you shift by 7, then you shift by 4, then you shift by 8, then you shift by 11, then you shift by 16. And I think if we keep doing all of these shifts, it's going to be harder to figure out because now we've chosen this long, complicated order.
Mm-hmm.
So do you think that this is going to be more secure if we do 17 shifts?
huh.
Because maybe that's one way to make the Caesar cipher more secure. Hey, I now chose 17 numbers. Do you have to figure out all 17 numbers I've done to decrypt it?
I don't think so.
What happens if you shift by 2 and then you shift by 3? What is that the same as? So if you first shift every letter forward by 2, and then shift every letter forward by 3, what is that the same as doing?
Shifting by 5.
Shifting by 5. So if you do a Caesar cipher followed by another Caesar cipher, it's just a new Caesar cipher.
Yes.
So if I do 25 in a row, I haven't made it more secure. It's still just a Caesar cipher. It's still just one shift. So what this illustrates is a wonderful idea that a lot of times you may think you're doing something to make it more secure.
You're not.
There may be a flaw, there may be a gap. And when you initially talk to kids, if you tell them, I'm going to do 100 different Caesar ciphers, good luck figuring out what I chose, they might be able to realize eventually, wait a minute, let's play with some cases. Let's see how hard it is to figure out 2 Caesar ciphers. 3, maybe they can detect a pattern. So I really want you to try to get things that you could try to bring into the classroom. All right, so now.
So I just am wondering, is it because they're linear, if you're adding a bunch of different linear pieces together, you just get another linear function in the end? Is that?
Yes, and the important part here is that all of the functions have a constant of 1 in front of the x.
Okay.
But even if they didn't have a 1 in front of the x, if you still just had linear combinations, it would just be some new a and some new b at the end. And so that same issue would apply here as well. You may not know immediately what that new encryption is, but exactly for the reason you said, linear of linear, when you compose, is going to be linear. And you don't leave the linear. Now, if you took a quadratic and put a quadratic in, now you would have a quartic. And so this is a either good property or a bad property about a linear function. Now, in the interest of trying to keep the calculations a little bit simpler, due to budget cuts, we are only going to consider a 6-letter alphabet, A, B, C, D, E, F. So the numbers 1 through 6. And we've decided that any B works as a shift. We want to see what values of A work in AX. So we're really going to just take our numbers, multiply by A, and we want to make sure different numbers go to different numbers. Can somebody give me a value of A that should work? What's the easiest value of A that we know will send different numbers to different numbers?
2.
2 is not the simplest.
1.
1.
One.
Because if we just take A to be 1, this is just the standard Caesar cipher, and just every letter goes to itself. So we claim it's enough to just take B equals 0. If we just choose different values of B that just shifts things differently. We can always handle those shifts. So let's take A equals 1, and we see that it works. We just get the numbers 1, 2, 3, 4, 5, 6. If we take A equals 2, it turns out it fails. 1 goes to 2, 2 goes to 4, 3 goes to 6, 4 goes to 8. But since we're wrapping around and we have 6 letters, 8 is really the same as 2. 5 goes to 10, which is the same as 4. 6 goes to 12, which is just 6. So we see that if we take A equals 2, it does not work. Similarly, if you try 4 and 6, they will also fail, because since 2 doesn't work, 4 is just 2 times 2, 6 is just 2 times 3. You can see those fail as well. If we take A equals 3, that fails. 1 goes to 3, 2 goes to 6, 3 goes to 9, which is the same as 3. So if we take 2, 3, 4, 6, they fail. If we take 5, 5 actually works. 1 goes to 5, 2 goes to 4. Can anybody see what 2, 3, 4, and 6 have in common with 6?
Divisible.
Yes, excellent. And so this is a great thing you can ask students. Hey, do you notice anything about the numbers that fail and the size of our alphabet, which is 6? And if they do notice, or if they don't notice, doesn't matter which, let's choose another value of A, another value of the size of our alphabet. Let's take an alphabet with 10 letters, with 12 letters, with 17 letters. And then maybe they might start to see there is a difference between prime alphabets and non-prime alphabets. That with a prime alphabet, everything will work. And with a composite alphabet, you will fail whenever you share a factor. And so you all detected the pattern. The A that work are those that are relatively prime to 6. So what do you think is going to work for the 26 letter alphabet we have? How many choices of A will be prime? Or conversely, which A will not be relatively prime?
13.
So 13. So we lose 13 and 26. What else do we lose?
2.
2. What else?
1.
Well, one will work, right? Because 1 just leaves everything alone. 2 won't work because 2 shares a factor with 26. So 2 and 13 share factors with 26. What other number shares a factor with 26?
12 and 3? No, sorry.
12 would work, right? Because
Yeah,
2 goes into 12 and 2 goes into 26.
right.
What else would share a factor with 26? So does 3 share a factor with 26?
No.
What about 4? Does 4 share a factor with 26?
No.
Well, what divides 4?
Oh, share a factor. Okay.
Share a factor.
Ability rules.
Yeah.
26.
So 4 would share a factor.
Okay.
6 would share a factor. In fact, all the evens will share factors. So the answers are basically all of the odds except for 13. So we have 12 choices for A. So for the Caesar cipher, there were 26 choices that we could have had for the shift. I am including the trivial shift where you don't move anything at all. If you want, you could say there's 25, doesn't really matter. For the affine cipher, where we do this AX plus B, there's 12 times 26, or 312. So this is more secure. There are now 312 things to try. Is 312 a huge number? No. And if we really needed to decrypt the message, we could try 312 different things. So could we go to higher degree polynomials? Oops. And so now you could try to ask your students, well, what would happen if we tried to go to a quadratic? So if we tried to go to maybe x squared as the simplest one. And the problem is going to be that we could have multiple roots. We could have two letters going to the same thing. And so as a nice exercise, you can show that there will often be problems when we try to go to higher polynomials. And then as a nice project for your students, you can say, choose different size alphabets and see when does ax squared plus bx plus c work? You know, are there choices of A, B, and C? How many choices are there? And this can be a little project for them to investigate. And if you can use a quadratic for some alphabets, then you have more coefficients to choose, and that makes it even harder to decrypt. And the more coefficients you have, the harder it's going to be. Okay. We're going to need the Euler-Toschen function a little bit later, so I thought this would be a good time to just quickly mention some quick properties of it. So we denote it by the Greek letter phi, and phi of n is the number of numbers from 1 to n that are relatively prime to n. So it counts how many numbers do not share a factor. So if I gave you the number 7, which is a prime, how many numbers do not share a factor with 7? So we will consider 1 not to share a factor, that there's no prime that divides both 7 and n. So they'll be called relatively prime. So 1 is considered to be relatively prime with everything. So if I give you a prime 7, do any of the numbers 1 through 6 share a factor with 7?
No.
No. So phi of 7 would just be 6. What if I gave you the prime 11? Do any of the numbers from 1 to 10 share a factor with 11?
No.
No. So we would get that if p is prime, phi of p is p minus 1. Then we could say, well, what would happen if we took the square of a prime? Well, what's nice is the only thing that divides p squared are p and p squared. So we just have to remove all the multiples of p. So how many numbers from 1 to p squared are a multiple of p? Or just start telling me, what's the first number that's a multiple of p?
E.
P.
And the next one?
Just P squared.
Not p squared. The first multiple of p is p. The next one would be 2p.
2p,
And what comes after 2p?
3p.
3p all the way up to p times p. So phi of p squared, we have p squared numbers, and p of them are multiples of p. P, 2p, 3p, all the way up to p squared. If I gave you p cubed, we would lose p, 2p, 3p, all the way up to p squared, then p plus 1 times p, and it would continue all the way up to p squared times p. So the last one that we need is if n is the product of two primes, then phi of pq is just going to be p minus 1 times q minus 1. And here's the proof. We're going to look at how many numbers share a factor with p and q. Well, since p and q are distinct primes, there's only two ways this could happen. You could share a factor with p, or you could share a factor with q. Which are the multiples of p? It's p, 2p, 3p, all the way up to qp. We lose q things. Which are the multiples of q? It's q, 2q, 3q. With my Boston accent, I will not say the next one, all the way up to pq. And so we've double counted, and so we have to add back pq because we threw it away twice. So the number of numbers that are relatively prime is we had pq, we lost q multiples of p, we lost p multiples of q, and then we add back pq. Okay, so this was the very simple initial alphabet ciphers. Any questions on the stuff up till now? So I'm gonna start, we'll take a brief 5-minute break so everybody can stretch and deal with all the life that is happening. And then we will resume in 5 minutes and talk about how we can try to find something more secure.